We now come to another integral obtained using differentiation. This particular one, I think, is for the higher level schoolwork scholars. So our integral, which I've denoted by u, goes from 0 to infinity, and the integrand is tan inverse ax times tan inverse bx divided by x squared dx. Now, this can be regarded as a function of a, so we'll differentiate it and we call the differential v. So v equals du dA, which equals the integral between 0 and infinity of x tan inverse bx dx over x squared 1 plus a squared x squared. That's differentiating the integrand with respect to b, and the x's partially cancel out, leaving us with integral between 0 and infinity tan inverse bx dx over x times 1 plus a squared x squared. Again, we can now regard this as a function of b. So we will differentiate with respect to b and write dv db, and that will, when we differentiate the integrand, we'll get x over x times 1 plus a squared x times 1 plus b squared x. And the x's will cancel out, leaving us with just 1 in the integrand, 1 over 1 plus a squared x squared times 1 plus b squared x squared. Now, we can use the method of partial fractions here, and I'll leave this to you, but it is not difficult to do and can be written as so dv db equals a squared over a squared minus b squared integral 1 over 1 plus a squared x squared dx, and minus b squared over a squared minus b squared integral 1 over 1 plus b squared x squared dx. And those are tan inverse functions, and that will give us a squared over a squared minus b squared times 1 over a tan inverse ax minus b squared over a squared minus b squared times 1 upon b tan inverse bx. So that's taken us so far. Now, putting in the limits, we'll get a over a squared minus b squared times pi upon 2 minus b over a squared minus b squared pi upon 2, and that simplifies to this, pi over 2 times a plus b. We'll now start reversing the process and integrate v, find the integral of this function here, because dv db is pi over 2a plus b, so v is pi upon 2 times the integral db over a plus b, which quite easily is pi upon 2 a plus b plus a constant c. We've got to evaluate that constant, and we use the fact that when b is 0, v is also 0. So we now get 0 equals pi upon 2 log a plus c, and so c is minus pi upon 2 log a. Substituting that in, we get v equals pi over 2 log of a plus b minus log of a. Next, we find u by integrating this function here. So u is the integral of v with respect to a, so is equal to pi upon 2 times the integral log a plus b minus log of a dA, which is pi upon 2 a upon b times log a plus b. I'll repeat that, a plus b times log a plus b minus a plus b, and then minus, this is for the log a part, a log a minus a, and then you have another constant there, which I'll call c dash just to not confuse it with the previous constant. And when we simplify that out, we'll get pi upon 2 bracket log a plus b times log a plus b minus a log b, a log a, I'm sorry, I'll read that this bit here again. pi upon 2 bracket a plus b log a plus b minus a log a plus c dash. The b being incorporated into the constant c, as it's a constant. But you see, when u is 0, when a is 0, so plugging that in, we get 0 equals pi upon 2 b log b plus c, and therefore c dash is minus pi upon 2 b log b. Now, we have assumed that the quantity a log a tended to 0 when a tended to 0. I haven't proved that, but it is true. That's the one part I'm just asking you to swallow for the time being. We can prove that, but not in this particular little exercise, because it is quite a long one, as you've already seen. And finally, we can now get what we want. U is pi upon 2 a plus b log a plus b minus a log a minus b log b. That is substituting in the c dashed over here. And we can write that as pi upon 2 the log of a plus b to the power a plus b divided by a to the power of a times b to the power of b. That finishes this. I hope you enjoyed that as much as I did. Thank you for listening.